is way too much email.
I'll do something else.
Well, why don't we get going on the second panel? So panel 2 concerns itself with maximizing the use of the International Space Station, and it's co-moderated by Oleg Kotov and Dan Burbank. Leroy introduced Dr. Kotov in the previous panel. As you know, he's a physician cosmonaut who's a veteran of 3 long-duration missions. Dan Burbank is a retired Coast Guard captain who's flew twice on the shuttle, and then on Expedition 2930 and was commander of Expedition 30. So, gentlemen, I hand it over to you.
Great, Jeff. Thank you very much. And it's a great honor for me as well to be here with you, and particularly on the occasion of the 10th anniversary of this great gathering. So the International Space Station is something that's near and dear to a lot of our hearts. For those of us who have helped to build it, for those of us that have had the great privilege of actually living and working there and doing the science that it was designed to be, was designed for, and for many of you who actually develop those science experiments and are payload developers, and for those of you who are the visionaries planning what we're going to do next. So the space station construction phase began in 1998 and continued probably through 2011 with the launch of the last larger elements. We certainly were utilizing it to a very great extent early on in those 10 or so years. But we only had a planned life of about 15 years. And now we've all agreed to fly it out to 2024 and use as much of the science capability a station can afford, and have that help us pave the way for the next steps we're going to take. But we're definitely past the halfway point for space stations utilization. From the perspective of getting to live there and work there, we have a 420,000 kilogram mass space station, and it's expansive. It's bigger than a football field, as you all know, and for a crew of 6, it's big enough that you often find yourself losing track of each other and maybe needing a half an hour or an hour sometimes to find each other absent the intercom system. It could support, when you look at the science that's on board, the capability with the facilities that we have, it's tremendous. We have, on a typical expedition for 6 months, a crew's going to execute 200 to 300 investigations. But I would argue there's a lot more that you could be doing if you could afford to have a bigger crew. Or there's perhaps a lot more that you could do with the station if you had the scheduling flexibility to use the crew that's up there to a greater extent. We're getting much better at that. We're getting much better at optimizing the crew time that we have, but we have a serious impediment, I think, from the perspective of the crew, in that we think of the space station as 2 space stations. We think of it as a U.S. segment and a Russian segment. And it's an arbitrary designation, really, because the space station and the things that go on aboard there don't care about segmentation. All the bad things that can happen, the fire, the depress, or the toxic atmosphere, things like that. It's one crew and it's one space station. And I would encourage, as much as we can, even, from the ground operation standpoint, to think of it as one space station. And for you, as the folks that many of you that are leading the science investigations we do on there and the programs, think of it as one crew and one space station, and we can do so much more. And I know we're doing a lot of this right now, and the 1-year mission helped a great deal. But we can immediately double our sample size, by virtue of doing that. And I think in the early days of station, we had a much more cooperative science program, just of necessity. When the limited amount of facilities and the limited equipment we had and the limited crew size, we did a lot more science together. We're now relearning how to do that again, and I think it's a very good thing. So with that, I would just like to go ahead and hand off to my co-moderator, a good friend, Oleg Kotov, doctor and cosmonaut, and very experienced, much more so than myself, on long-duration space flight. And we'll kind of, person by person, introduce ourselves, I think, and give you some initial thoughts, and then we'll moderate questions after that. Oleg.
Okay, sounds like a plan, I guess. Hello again. I just completely agree with my friend, with Dan, about the ISS, about International Space Station, about our cooperation and research and performing science aboard the station. And we completed phase when we construction phase, and since 2011 we are in a utilization stage. And as a result of utilization, we finally recognize that there's no sense to divide station for two parts, Russian and U.S. segments, because we designed like a balanced contribution committee in the beginning and decided, okay, we need to divide station to two parts and start counting the time, crew resources, supplies, everything. And as a result of that, we lost efficiency of the station. And just a few years ago, our manager just figured out that we got a problem, and we built a huge laboratory, but efficiency is not very good. And I'm lucky to say that, so we're in a good way. We now in the phase like a reunion stage for science. We started a big program for joint experiments that we perform together as a one crew aboard the station, and sharing all science equipment, crew time, any supplies, everything, and do a great job. And I think we're in the right way now. And so I pass word to you again to introduce.
So I guess we could just hand off to you, Mike. Mike, a lot of experience with space shuttle missions and expeditions as well, and for a year at least, I think Human Research Program, director as well.
Mm-hmm. This is space improv, right? So
Yeah.
we're going to keep this very informal and very casual. I came, I saw, I flew. I've actually had the chance to wear a lot of hats at NASA. I came as a flight surgeon in the early 90s. I'm board certified in internal medicine, aerospace medicine, and was lucky enough to fly a couple of flights, one long, one short duration. I want to, as we're talking about maximizing the use of the ISS, I also want to talk a little bit about the apologetic of the ISS. And we talked about getting bogged down on the moon. In the early 90s, I was one of many, many people working the Shuttle Mir program who was called to Crystal City, Virginia to talk about next generation station. And we had, others had been laying the groundwork. I think Mr. Abbey was part and parcel to that, of International Space Station as a follow-on, and we hadn't even started flying the Shuttle Mir program. And there were a lot of discussions at the time, should we go to Mars? Shouldn't we just spend all this money and go to Mars? Why are we doing this? Why are we going to get bogged down in low Earth orbit? And I was asked a lot of questions from a medical standpoint. Do we really need to rewrite Guyton's textbook of physiology for zero gravity? Well, the answer at the time was pretty clear, no, because my experience base was limited to the literature at hand. We need to focus on those targeted problems we know happen in zero gravity, bone, muscle, radiation, whatnot, and we sort of did that. Let's fast forward to now. We've been flying station for 16 years, and our big risks, bone, muscle, radiation, et cetera, some of those are still there. Some of them have solutions, but they've been joined by another big risk, which is the vision intracranial pressure thing, that a few years ago we didn't even know existed. So we're not talking about VIP this year, and we don't need to talk about it scientifically, but philosophically, it's prominent. It's a big problem. It's pervasive. It affects critical neuroanatomy. It's something we really need to understand before we venture further. And we only know because we have a station with accumulated long-duration flight rate and the tools aboard that help us to characterize it and the support infrastructure on the ground. So it begs two questions. Are we going to solve this, our now second biggest risk factor, before we can go further? Number one. Number two, what else are we missing? We've been dorking around in space for 50 years, and one of the biggest, most prominent physiologic effects of spaceflight we missed all this time. So there may be something that big. There's probably a lot of other things somewhere between VIP and something that's fairly non-consequential that we haven't seen yet. So if you were to ask me the same question now, should we rewrite Guyton's textbook of physiology for zero gravity? Well, the answer may be, yeah, you may be crazy if you have the chance to do so and you don't. Because years from now, we'll be thinking, boy, I wish we had done that on station, or I wish we had looked at that, I wish we had investigated that. So station is really doing what it was designed to do. It's looking at the risks that we know and helping us to characterize and mitigate them, but it's also finding new risks. So it's huge. As we talk about maximizing the use for station, we need to be VIP hunters, hunting for other problems that we just haven't seen yet because we hadn't had the right tools or applied them. And then the other point I want to make as we pass it down, having been either a member or a watcher of the astronaut office for the last 25 years, it's hard to believe, I can tell you that the face of the astronaut office has changed drastically, and I think in a very positive way. When you look at the big things that astronauts strive for in their careers, launches, certainly those spacewalks, robotics, docking, anything manual. We've added a new thing to that, which is discovery. We've created, I think, a generation of science geeks. And that's both philosophical and tangible. Tangible meaning every astronaut to be qualified to fly now must be certified in generic rodent skills and certified in biomedical basics and show that they know how to take imagery and do microscopy and whatnot. And that's a new thing. And when people are up there, the biggest thrill of a mission, I'd say it was right up there with a spacewalk, is seeing something for the first time, discovering something new. And that's the exact kind of mindset we want to take further than low Earth orbit. And that's been really, really exciting to see. There's a gratification in discovery of new things that we just hadn't seen for a long time. So that's our current generation. So we have built those two things, I think, the ability to find things that we couldn't before and a discovery mindset that I think is another thing that we want to maximize on station. Now, because of the people downstream, I'm going to pass on now and not talk about some of the hardware and data sharing things, but those are tools that we need as well.
Okay. Good morning, everyone. Mark Mulqueen, Program Manager for the International Space Station for the Boeing Company. Believe it or not, I started on Space Station back in 1987, and I've had the luxury of multiple phases of station, both in redesigns, but laying out designs and testing, and then the assembly and operations of ISS. So I'm very fortunate in my career. Sometimes we take ISS for granted, 16 years, hundreds of crew members up there, but ISS to date's gone 2.5 billion miles traveled. It goes to the equivalent distance to the moon and back virtually every day. The orbits and cycles and fatigue cycles on ISS, it's very, every 90 minutes is a full thermal cycle, and those cycles add up to millions and millions of cycles. We understand how to do that. You talked about 15 years of life and maybe getting the end of that. ISS is much like an airplane. In fact, we understand every airplane that we fly on and where we go, the cycles that we're doing with a hard landing, a normal landing, the elevation, the pressure. We understand how that is done on airplanes. We do it continuously for all the airline companies to make sure they know when the end of life is near for their vehicles. And they certainly have margins when they actually sell them to third world countries and other things because the vehicle still is usable. ISS maintains a factor of safety of 4 on life. And right now we're going to prove it's going to go 30 years. Charlie's given us the contract. Boeing's halfway through that. And of course the early modules are what we looked at because they're on orbit longest. The later modules won't even hit their 15 years until 2028. So those go without saying. So ISS has so much capability in it. And today it is the cornerstone for human space exploration. Tomorrow, Orion will be flying, and it's SLS, and certainly the launches for SLS and the discoveries that Orion will hold will be the next cornerstones for human space exploration. But today, it is International Space Station. There are things going on ISS from the crew and all the science they've done that Hope Crystals, it's the Japanese module, did clinical trials. They're in clinical trials now. This is for treating Duchenne's muscular dystrophy disease, and certainly is something on orbit that we discovered, the water molecule, that we can't see on 1G. And so once they discovered that, they were able to separate that out and determine what it was and how to develop a drug that was more benefit to the humans that are born with that disease and to give them quality of life and extend their life much longer. Those trials are in now with humans, and I expect that to come to fruition in the near future. Amgen has probably exceeded $1 billion in revenues now on Prolia, which you probably see advertised on TV, and Xgeva, which help osteoporosis. Of course, we've been talking this morning sessions about study of bones and human effects of zero-G. So those studies have led to discoveries that help us life here on Earth. Lots more to be had, and we can sometimes expect ISS to have instant payback for those discoveries. But as you look at space exploration over the last 50 years, computers, our cell phones, things that we have, and miniaturization do take time. And they get into industry slowly and eventually, and so those things are still ahead of us. ISS has had over 100,000 orbits around the Earth. We've served over 26,000 crew meals. Think about that, all your kitchen uses. We've had over 1,100 hours of extravehicular activity, both the astronauts and cosmonauts on space stations. So understanding those effects, the discussions this morning on the suit and the pressures, even today, suits are a challenge, we know that. And as we go to deeper space, you have less ability to change those suits out, so you need to make sure you have first-time success on those suits, and we understand how they work and keep our crew safe. Going to Mars is not about a one-time mission, and that was some of the things that we all in this industry looked at for Elon's discovery or his plan. It's about quality of life getting there, it's about quality of life getting back, and quality of life here on Earth. So if I just send a one-way mission, there's not many that will volunteer. There will be some, but if I promise you at least a return trip, but not quality of life on Earth, would you really want that mission too? Because it's kind of limiting your life. So you have to really look at the whole life cycle and make sure it's safe. And this industry is non-forgiving now. They talked about Apollo having the ability to survive a loss of humans. Today we don't accept that. And so when you look at the investments that NASA and the contractor communities have to put into our systems to make sure that don't have damage and failure and loss of life, it is extreme. And so the testing and the way we build things today, and Station did a great job to help us modularize a pre-integrated unit. If we got to space, we plugged the units together and turned the powers on, and they would work, because they did extended testing here on the ground. If I had to build the whole ECLIS system and the whole comm system from ground from scratch, so to speak, in space, it would take you forever. The crew can never do any discovery. They'd be building these little things and soldering things. And so when we talk about pre-integrated, it is very key. Expansion modules are great. They give you a lot of volume, but nothing comes pre-integrated. You then have to fold everything together and put it to place. They are a great idea for expanding the human's environment of safe haven to float around, maybe even putting in some sleeping quarters, but to expect that to carry all your power, your ECLIS, your food galleys, and other quarters, it's probably unrealistic, at least in deep space. Maybe Leo could afford the crew and time to do that. But as we look for exploration, we've talked a lot about the human. And if we got out of low Earth orbit today, or even in 10 years, and we don't have the other platform out there, would the U.S., would all the countries still invest? Would ESA still invest in their ministries and funding? I think if we step out now, the risk of going back to human-tended deep space platforms is probably going to be at the greatest risk. And so keeping ISS going and allowing us to continue discovery for improving life here on Earth, allowing us to feel safe and how we keep humans alive in space, and how we improve their quality of life and make sure that we don't have eye problems and bone structure problems and muscle atrophy. It's going to be key that we keep understanding it. So ISS, you could hand it off to a commercial platform, but our ability to generate revenue is probably not really well understood to the point that I could sustain it as a contractor. It's probably going to require investments of the U.S. governments and other governments. We stimulated commercial cargo delivery. If we got rid of LEO platforms, commercial cargo delivery goes to zero because there's nothing to go to right now. We're stimulating commercial crew. Boeing is very fortunate to be building the CST-100, the Starliner. We're making great progress on that. Our destination today is ISS, will be ISS. If there's other platforms, it'll be outstanding because we have a module that has 10 cycles on it. The same vehicle is going to go up and down 10 times, and we understand how to do the fatigue and the safety of that. That was our intention, to reduce costs. But if I only go once a year to ISS and I have no other platforms to go to, or if ISS ends early, that whole investment by NASA and by the contractor communities, including SpaceX, would be at risk. There's no platform to go. It would have been a lost investment. So, Commercial Crew is making great strides overall in the program. NASA with both their contractors. Boeing CST-100 Starliner is past all the critical designs. It's into 2017 as our test environment. We have all of our subsystems are delivering, qual tested, and get delivering so we can build up our qual unit. Late next year, we'll be into full qual testing, which includes thermal, vacuum thermal cycle testing, acoustics, power on, comm, all the tests necessary. Our structural test article is already completed. It will be starting early next year, testing, pushing, pulling, pressurizing. The service module is already delivered. It's already been hooked up and ready to be tested structurally. In 2018 is the first non-crewed flight test, and then the crewed flight test. So we have a lot ahead of us. We have a lot of the great news that everybody's looking for. The headlines of successes is probably out a year or more. But the companies, both Boeing and SpaceX, are designing this, and we need a platform to go to, and we need to prove the viability of this business, and then hopefully it stimulates other platforms. ISS actually is still expanding. The Russians are going to bring up the MLM in probably a year from now. We're talking about the solar power module. There was talk about a commercial module from industry that would supplement the laboratories and the space volume in ISS, and those are very key to have longevity, to not only put your business case together, but to build your unit, test it, launch it, and get some results out of it. So it's probably requires more than 10 years to get the business case to really close on those things. ISS is truly a discovery. It's an international cooperation where the relationships that was talked about this morning also are so strong that engineer to engineer, contractor to contractor, agency to agency, we put out the other politics that go on, and we are united as a team. And I've been to Moscow probably 50 times in my life, and every time I meet a new person who's interested in conversations and solving studies or technology challenges or risks or testing, and I've never had an instance where they're not respected, each community. I know they come to the U.S. quite often, and we have great not only technical meetings, but we have social endeavors afterwards. It has created such a robust population of engineers and scientists across the two countries and with the Europeans and the Japanese that it is truly a treaty that needs to continue on, and will launch our space exploration, deep space activities. This morning we also talked about lessons learned, and we didn't do something from Gemini to Apollo. If we didn't do Gemini, we wouldn't have brought it into Apollo. Lessons learned are the hardest thing to transfer between programs, and it is very hard transferring from shuttle to ISS, from ISS to cislunar to Mars. Those things are key. NASA's the glue that has that, because sometimes contractors change out. Today it was Rockwell, today it's Boeing, tomorrow it could be some other contractor building things. So the transition of lessons learned, what's successful, how do you do it, is so important. And as we go to deep space, it better work the first time, because repairing that will be even more embarrassing for our communities to pull off than just even getting there, launching safely. So with that, thank you very much.
Okay, and let me introduce the next speaker, Irina Ogneva. She is PhD and Chief of Biocells Laboratory in IMBP. Irina, пожалуйста.
Thank you very much. First of all, it is my first time here, and I'm happy to be here, but if you don't mind, I will continue in Russian. На мой взгляд,
to my opinion,
максимальное использование станции
use of the station right now
когда мы снизили число,
especially now when we have
членов
less
российского экипажа,
Russian crew members on station is kind of cumbersome, difficult.
много вопросов всегда
There are a lot of
возникает
questions that come up usually with fundamental science research, and it is obvious, however, that the Mars mission would not be possible now, because not only because we don't have some technical verification, but also medical and biological support for this kind of mission. That is why the station is a unique capability to expose various microorganisms and also restoration of those in gravitation on Earth. And if we can do it in microgravity, that would be great. Maybe some kind of method is developed. That would be nice. In Mars, the gravitation is lower than on the ground, and perhaps what we are developing right now will still work over there. Probably we always ask a question, yes, the human beings as well as dogs have been flying from the beginning of the space program, yet lately we have received a lot of screening methods of research that allow us not to find something by search and error, but to have a complete picture at the beginning already, and that would not be possible without fundamental research that is being carried out on the station. We have this unique capability, we have to use it in full. Right now, we have an amazing experiment, rodent research, that is NASA and IMBP combined project. That is an amazing program, rodent research, that is allowing us to receive unique data. Already now, we are able to separate tissue, other things, some unique data that would not be possible to receive before. Even here, in this combined research experiment, we are still encountering a lot of problems that have to do with time buttering for the crew time on board. On the US side, it would not be possible to carry out this experiment without pharmacological companies' participation that help us financially for this particular program. At the same time, I believe maximum use of the station would probably be better if fundamental research is given more chance, because that is the foundation for the practical application of what you have. We probably know that it's unlikely that Einstein was thinking about application of his research when he was writing grants. So he would not be putting something that it would be helpful for humanity in the future. Every scientist right now is trying to get some financing for the funding for fundamental research, and we try to explain how it is going to be beneficial for, in our case, humans to be delivering themselves to Mars. Everybody understands that there is a risk over here, and I'm just for fundamental research in general. I believe it is important to pay more attention to fundamental research. That is why probably not to far in the future we will receive a global amount of data that will help us to make a breakthrough in finding the methods of reducing risks and helping humans to overcome microgravity in the future. Thank you.
Thank you. And the next panel member is Dr. Bill Pulaski, who's the current director and has been for 4 or 5 years, I believe, 4 years, of the Human Research Program. And the key elements there, of course, and many of you know this already, but ISS medical project, space radiation, a key thing for us that's often recently become a limiter for how long crews can spend on orbit. Human health countermeasures, exploration medical capability, paving the way for how we're going to provide medical support that crews will need when we will leave low Earth orbit, for example. BHP, behavioral health and performance, and human factors and habitability, all key things. Many of those we're actually using as we do work on designing and developing these new vehicles we're about to fly to.
Right.
Bill.
Okay. Thank you, Dan. Yeah, I've been a researcher at NASA for over 30 years now, and for the past 4 years, I've had the privilege of running the Human Research Program. And as Dan was pointing out, it's a fairly robust program. We have a fairly large budget, but we have a very daunting charge, which is to figure out how to send people safely to Mars and get them back home and let them have a high performance while they're there and have a very good life afterwards. So there's a lot of pieces to that. We don't have a lot of tools to go and answer those questions, as we've already heard today. One of the best platforms for looking at answers to these questions is Space Station. And certainly for the low gravity issues and the hostile closed environment issues that we have to deal with, Station is good. It's not so good for simulating the radiation environment or the isolation and confinement. Every crew member has a cell phone in their pocket, and they can talk to their family when they want. They're in constant communication to the ground. So we look for ground facilities to do some of those studies. But we do use the station very heavily. In fact, on the U.S. side, I'm probably the largest hog at the trough for crew time. We average about 250 to 300 hours of crew time every increment pair. The most recent increment pair, we had 377 hours of crew time. The only USOS entity that gets more crew time than us is CASIS, which is a commercialization group that is trying to figure out how to commercialize low Earth orbit for scientific research. So the work that we do there is coordinated with our international partners. There's been a lot of talk about how do we do that coordination. There are actually 3 separate groups that have overlapping membership that we work with. The one that's probably the most prevalent for Station is called MERPI, which is the Multilateral Human Panel for Exploration. It's run by John Charles from the U.S. from NASA and Valery Bogomolov from IBMP. In Russia, and all the spacefaring partners on the station participate in that, and we talk there about standardization, about sharing data, about the ethics issues of sharing subjects, and also how we can do joint experiments. We also have 2 other more long-standing groups. One that's called ISLSWIG, or the International Space Life Sciences Working Group. We just came back 2 weeks ago from Japan, where we had the 51st meeting of that group. It meets every 6 months. So we've been working together for more than 25 years to try and coordinate not only flight experiments, but ground experiments, and also solicitation. So we do joint solicitation so that we can leverage each other's assets towards common problems that we're trying to solve. And then finally, we have a joint working group with our Russian counterparts that we usually get together once a year and talk about common interests as well. And the next of those will be coming up in Moscow in December, about a month from now. On the station, we're looking hard at questions that are pertinent to to exploration. So we look at some fundamental questions, but we also look at things like we have a group that goes to every landing site. We have something called the field test experiment, and we have a member of the team who schleps out a bunch of research equipment to the landing site, and when they set up the tent to bring the crew in, the medical tent, there's an experiment set up, and crew members, both Russian crew members and U.S. crew members, participate in performance measures of how well they can perform right after a 6-month mission. This is quite relevant to what kind of performance you might expect after a 6-month mission to Mars, except the landing crew isn't going to be there, or the welcoming crew. So what sorts of locomotor issues do they have, what sort of cardiovascular orthostatic hypotension issues, and so on. And we've now been able to categorize that for the last 7 or 8 separate increment pairs. So we're starting to accumulate a lot of data that we're sharing with the Russians on that. We also are looking at exercise. Exercise is probably the primary countermeasure for anti-gravity activities, and so this is the bone, the muscle, the cardiovascular, and the neurovestibular systems. Exercise doesn't really help neurovestibular system, but it helps the other systems, and we're pretty good at doing that. But if you've ever seen the exercise equipment on the station, you'll know that it's never going to fly to Mars. So we are working on more streamlined systems, and I just actually had a presentation with my boss yesterday where I showed him, unveiled some of the design characteristics for a new servo-controlled, motor-driven exercise device that will be able to replace the ARED as well as the aerobic devices that we use in a package that's about 1/10 of the volume and the mass of the current exercise equipment. So this is something that we'll be testing on station, probably starting in 2019. We just last 2 weeks ago, last month, Kate Rubins installed in the station a set of solid-state lighting assemblies. She put them in the crew quarters. This is probably the way forward for monitoring circadian rhythms or for controlling circadian rhythms in flight. These are LED devices that are much brighter than the lights on station. They use less power, but they're much brighter. And we know that light intensity can affect the melatonin regulation of the body. But they also have another characteristic, and that is that they have tunable spectral characteristics, so that in the morning when crew members wake up, they can be organized to be shifted towards the blue end of the light spectrum, and in the evenings before bedtime, they can shift towards the red end of the spectrum to help taper and start up quickly people for their circadian shifting. So we will get a lot of runtime, at least 7 years on the station with these. There is another set of 11 of these assemblies that are scheduled to go up on HTV6 in December. More recently, we've been doing some very interesting joint experiments. I know you're all aware of the 1-year mission that we just completed with our Russian counterparts. You may not know about some of the complexities of the scientific experiments that we did, not only with our Russian counterparts, but also with other members of the international life sciences team that flies crew members on station. Probably the most complex biomedical study that was ever done on station was done as part of the 1-year mission. It'll also be done on some 6-month missions coming up. It's called the fluid shifts experiment, and it required 3 times during the 1-year mission 4 days of operations, 2 days in the U.S. laboratory and 2 days in the Russian segment kitchen, where they have a Chibis device, which is a lower body negative pressure device. And this study is designed to look at the VIP problem that Mike mentioned earlier, and one of the key hypotheses is that the VIP is related to fluid shifts and long-term fluid shifts of fluids from lower body to the upper body, increasing the intracranial pressure. And so by bringing people into the Russian segment and sticking them in the Chibis and pulling a lower body negative pressure, we can move fluids out of the upper extremities and then look at the dynamics of the cardiovascular system under those circumstances. Let's see, what else have I got? Oh, and another thing that MRPE has been working on is a set of standard measures. That is a set of measures that we would do on every single crew member that flies. At the current time, when we do an experiment, if it's a cardiovascular experiment, we get some cardiovascular data, but if the crew member didn't sign up for a bone experiment, we get no information about bone. But if we have standard measures that cover all the systems of interest, then we can increase the N across the board and reduce some of the requirements from individual experiments that come aboard. The U.S. side has developed a first set of standardized measures, and now the MRPE group is looking at how to internationalize that set of standard measures. I think that's probably most of what I wanted to say. I will mention that as a platform, access to the station has been extremely good for us. The station program office gives us a high priority, and we have a good team, our ISSMP team, for integrating science into the station and getting data back and getting it passed out to our investigator teams as need be. One of the things that is somewhat daunting for us when you think about a mission to Mars that might be 30 months in duration, and you look at almost all of our experience is in 6 months. There's an awful lot of space that we don't know much about. We have experience now with 2 crew members who have doubled the time in exposure to low gravity. So we think that it's really important for us to explore that space more as we can on station. So we have been proposing and trying to work out the details of an additional 5 missions that would be 1 year in duration with crew members, with 2 crew members aboard each one. So we have a sufficient N to be able to answer questions and to look for other things, as Mike pointed out, that might pop up that we hadn't seen before, and also to verify that the kinds of countermeasures we have that are successful at protecting bone and muscle during 6-month missions will continue to protect it during the longer 1-year missions. So we have a lot coming forward. The station, as we've discussed, is slated to come down nominally in 2024. Mr. Gerstenmaier has talked about that being a bit squishy of a date, and the squishiness is going to depend on 2 things. It's going to depend on whether the answers to the exploration, physiological, and behavioral questions have been answered to the extent that we can answer them on the station, and on how well the commercial crew programs that we're also facilitating have been able to progress. And so if we answer our questions and get the commercial crews moving earlier, it might not be there till 2024, and if it goes longer, then it can be up there at least until 2028, we understand. So there is a little bit of flexibility in that endpoint. At the same time, we're looking to the next generation of vehicles, and we've heard about SLS being developed and the Orion vehicle being developed. What you haven't heard so far is that we're also working on a deep space habitat design, a habitat that would be in place in cislunar orbit for a very long period of time, distant retrograde orbit that can allow it to be stable for up to 80 years. I don't think we'll be using it for 80 years, but these are very stable orbits that the Orion would go to and mate up with and sustain crews for longer periods of time. It also could be a stepping off point for international partners who might want to go to the lunar surface. Whether the U.S. goes or not is a question, but we know that many of the partners want to go to the lunar surface. So having a station of sorts or a deep space hab in that environment will be very good. From a biomedical perspective, being able to look at crews in cislunar space and in deep space will enhance our ability to look at isolation and confinement, to look at autonomous operations. Somebody mentioned earlier the time delays, but time delays come with autonomous operations, and how well can crew members work and do things that they need to do if they don't have good communication with the ground, or if they have 20 minutes of time delay. Then we won't have that kind of time delay in cislunar space, but eventually we will for Mars space. So we can work on how we do the autonomous operations there as well. So I think there's a lot of opportunities that are coming up. We're already trying to figure out how to outfit the deep space habitat and what kind of research we might want to do on it. Crew numbers are probably going to be small, but we'll at least validate the things that we're testing and learning how to do on station in cislunar space in the future. So I'll stop there.
Bill, thank you. And our final panelist is Quechee Wakata, JAXA astronaut, flown aboard 4, I believe, space shuttles, 72, 92, 119, 133, 2 of which I think took you to and from station for his first mission, 18, 19, 20 expedition. And then he flew aboard a Soyuz for his last one, during which he was also the first Japanese commander at the International Space Station on Expedition 39.
Thank you. It's an honor to be here. Yeah, today's theme is maximizing the use of the ISS, and of course, international cooperation is the key in here. And but I remember, as NASA Administrator Charlie Bolden here mentioned, that in Guadalajara, Mexico, when we talk about our activities beyond low Earth orbit, it's important for each partner countries to clarify its own flagship missions, exactly what we want to do beyond low Earth orbit. And then it's important that each partner help each other to accomplish that goal of achieving the flagship missions. And in that aspect, in exploration, Japan is focusing on developing a regen ecosystem, having the capability for planet surface mobility, as well as deep surface rendezvous and stuff. But in the ISS utilization, it's also important, for each partner to achieve its own flagship missions. And we have a lot to accomplish before the 2024 comes, or even beyond. And Japan has decided, the government of Japan has decided to extend the ISS operation beyond until 2024. That decision was made in December. It was a big deal to convince the government and the stakeholders for us to continue, and it was a great news. And we have to show the benefit of exploration, or the ISS operation, to the public in Japan in order to extend this mission to 2024. And so the question is, are we utilizing fully the space station on the ground and also in space? I was fortunate to be able to fly with Dr. Barrett on Expedition 19 and 20. Before that, I was an Expedition 18 crew member, and there was a huge difference between 3 crew member stage and a 6 crew member stage as far as the amount of science that we were able to put in. And soon, as Ms. Ogneva mentioned, that the Russian crew members reduction could happen to 2, but hopefully we'll come back to 3. Eventually, we will have 7 crew members, and that's a lot of people. And we need to fully utilize the crew members. And as Oleg said, when we had only 3 crew members, we were integrated as one crew. Americans and Russians worked together, and Japanese also. However, when we went to 6 crew members, somehow it was like a segmented operation. And maybe it's efficient in terms of training and facility planning. But in terms of fully utilizing the crew members' assets on board, it's very expensive to use the crew time. And I think more integrated operation of the crew members on board is, I think, more helpful to fully utilize the space station. Russian Joint Research, Mike and other folks are involved. I think this is a great way to achieve this, and Japan is cooperating with the Russians on the protein crystallization experiment for pharmaceutical medicine development, and has been going very well. And I think we can expand that joint utilization more in order to fully utilize the crew asset, and then utilize the unique capabilities of the ISS that each partner has. For example, Japan has integrated capability of robotics with non-human airlock, from which we deployed so far 147 CubeSats. And that's the only capability that the ISS has at this time. And we deployed the first satellites from many countries, like the Philippines' first satellites, Lithuanians' first satellites, and stuff like that. So that is contributing to the capability building for developing countries in the space arena. And protein crystallization and also aging-like phenomena studies. Dr. Satoshi Furukawa is leading that in JAXA. So those are the flagship missions for Japan, and we need to integrate those operations more among the partners in order to fully achieve, in order to more efficiently achieve those goals. And last December, when the government of Japan decided to continue the space station operation until 2024, Japan and the United States established a new framework of OP3, that's an Open Platform Partnership Program, that both countries' researchers can utilize the assets of the space station together. Japanese experiment laboratories, half of that is a U.S. Right to use, but as far as research facilities, usually the Japanese research facilities are used usually for the Japanese, and then the other part is used for the Americans or Russians and Europeans. However, those are segmented. So this OP3, the new platform partnership program, allows the researchers from both countries to utilize the facilities in order to achieve more. And I think this is a new framework, and it's usually tough to establish new frameworks, same with the Russian joint research as well. But I think we need to open up and challenge ourselves to expand this kind of new operation or like a framework to cooperate each other. And Japan is working with the United Nations Office of Outer Space Affairs to utilize that Japanese roboticom with ALOC for deployment of satellites from developing countries. Like we have first, last month we decided to launch Kenya's first satellite from JAM, and that's through the United Nations. And so as spacefaring nations, it's also our duties to open up the opportunities to utilize a space station to other countries. And maybe education is a good field to open up the opportunities to the developing countries. Like Japan is working with Asian countries. Last month we did educational events with 6 Asian countries utilizing the Kibo module. And so this is another new framework that we can contribute for capability buildings of the developing countries in the space arena. So, and also, since this is a medical summit, one thing that I would like to emphasize is that radiation monitoring is something that we can have more, I think, cooperative effort together, since the model that we have on board or utilizing right now is a very conservative one. And in order for more younger astronauts to be able to fly to Mars, if we have more accurate model from which we can extract the limit of our life in space, I think, JAXA is launching on the December launch of HTV6 new active radiation monitor, and utilizing that kind of capabilities with US TPIC, I think we can establish more, I think, efficient real-time monitoring capabilities. So there are a lot of arenas that we can work together to improve our capacity for exploration. So the bottom line here, I just want to emphasize that setting up a new framework of cooperation is tough, but it's really worth it. Thank you.
Great. Thanks very much, Quechee. We have a hard stop time at 12:30, so we have about 25 more minutes for questions. I had a couple of things, maybe some follow-ups that I could weigh in here, but I imagine you probably have quite a few questions as well. I guess one thing I would just say as an observation is that, Space Station finally affords, at least for the U.S. space program, it affords us the ability for researchers to not just have the keys to the laboratory, 10 years hence for 2 weeks or something like that. And it also affords you the opportunity to have collaborators on board, and it allows you to design the research not necessarily with a presupposed end so that that experiment can be turned on, run its course, turned off, and you get the data that you expected all along, but it allows you to do something a little more appropriate and proper. And science as it's meant to be, more open-ended. So that may be a way that we can, we're doing a little bit of it, I think, aboard Space Station. We're quite a bit better than we were during the space shuttle days in that respect. As we look at the things that we do on board, human research, and I know that, again, this is a space medicine summit, the human research that the U.S., that NASA does, is principally focused on how to extend human presence into deep space, answer those questions. But there's certainly a lot of other work that's being done that also has applicability back down here on planet Earth as well. Mike, for you, are there areas beyond things like VIP that are newly discovered threats to deep space or long-duration spaceflight, new things that you would like us to see us expand our investigations into? Are there certain areas that are ripe for review?
Well, let me ask a question you didn't ask, the question you meant to ask first.
Thank you.
That's a good question.
It's spooky how he does this. He always has. So yeah.
So you mentioned new things besides VIP, but let me just posit that when we look at VIP, we're finding things that the human body does that we didn't know it could do. We didn't know it would do, and we thought, well, let's look at the ground literature on the circulation of cerebrospinal fluid to help answer this. Well, it turns out we don't know nearly as much about the circulation of cerebrospinal fluid as we thought we did. And so when you look forward, when people say, well, why do you need to do this in space? There's no, Peter Norskier here is my physiological backup. I don't think there's a tenable notion that we could have learned everything about physiology on the ground and been able to predict VIP. We're learning things about physiology that we just can't learn because when you have to get in this unique environment to do it, and those are transferable to any environment. I would say 0G, 1G, and everything in between, and probably a little bit more. So I think what I think you meant to ask was if we were to look at two lines of research, we've got to have a strategic fly-off. Bill Pulaski and his international counterparts have the unenviable task of using this time-limited resource to burn down the risks of what we know, bone, muscle, radiation, et cetera. We have to know this stuff. At the same time, you have to do discovery science. And if you were to, and we get criticized for that a lot, but if you were to go to Francis Collins, who runs the NIH, and say, we're going to fund your basic research, but we're only going to fund the lines of research that lead to breakthroughs, we're paralyzed. We're stuck. So you have to have a coherent basic research portfolio also, independent of what you think you know on the ground, because VIP and other things have taught us that doesn't necessarily apply. And so a strategic, that's what I'm saying, rewrite guidance for zero gravity. There may be reasons to do that. And so you need both. Right. And everything we learn there will have ground applications. And now we're looking at ground physiology a lot more keenly to help us try to explain things on orbit.
And Mike, if I could just add a little bit to that, there is a separate NASA program, the Space Biology Program, that is actually focused on discovery research, and they have a different charge from HRP. There is some overlap, and we try to take advantage of that, but they are really looking for trying to understand the role of gravity, for instance, in physiologic development, in physiologic processes. So they're answering fundamental questions. Their time on station is quite limited, though. CASIS also brings forward some very interesting novel approace to understanding terrestrial biology in a space flight environment, and trying to understand how to commercialize things that we can't do very well on the ground that we might be able to do better in space.
I will give you one concrete example, because you did ask for that, and that we know that there's a population of ground folks who have intracranial hypertension increases, and the standard surgical procedure is to relieve that pressure with a shunt that goes between the cerebrospinal fluid and the peritoneum. Well, a lot of people don't respond to that. They still have some of the vision changes, the anatomical changes we see. We didn't really understand why, but now we're starting to understand that these blind alley effects that we're seeing on orbit commonly can start to explain some of these things. So our mitigation strategies may be very applicable to these non-responders.
Very good. So if you're going to maximize utilization of space station, one way certainly is to add crew members where you can. And I think we saw, as we consider going from 3 USOS crew members to 4 USOS crew members, there's a certain amount of overhead that it just takes to maintain space station, and it is just the steady state thing, and it takes a good bit of the time of 3 people in the U.S. segment, if you forgive me for using that dreaded word. But if you had one other person, all the other systems are running. You're maintaining the WHC, you're tweaking the catalytic reactor for the seals are bad, you're doing all the other things you have to do. You're preparing for spacewalks and doing robotics and doing onboard training or whatever else it happens to be. But that one other person is almost free from the standpoint of utilization. So suddenly, if your target utilization numbers, the ones we typically shoot for, around 40 hours a week but we typically get 50, maybe 60 hours. Getting another person's 40 hours free is a huge plus up in the utilization of that station. It's a shame to be living there and to see racks that are idled just for the lack of somebody's crew time to be able to activate them and interact with them and so forth. So one of the big limiters for that, of course, we discover really is the carbon dioxide environment. So our ability to scrub carbon dioxide is pretty limited. Or when you start to push the hardware to get it down to the levels that we think are appropriate, it's really, really hard on the hardware. Roughly on station, I think we're at probably 10 to 15 times the level of carbon dioxide that in a terrestrial environment you're used to. And some folks are fairly sensitive to that. And there's the stuffiness that crews report, even the foggy cognitive ability, the space stupids is another thing maybe. But there's, and it's possibly that it plays into VIP too. There's a theory maybe that it does as well. So on the system side, Mark, maybe you from the Boeing perspective and the engineering perspective have some ideas on the things that we could do to take care of the environmental control challenges that are limiting us in a real fundamental way, crew time wise.
Yes, absolutely. As we go to deep space, the systems that are working flawlessly and meet the standards that the crew expect and is going to be critical. ISS has had its challenges in the environmental control, life support, mostly CO2 removal, even in our oxygen generation system. Certainly, some of these systems were generated, there's not many needs for us here on Earth. Mother Nature does a great job provide that environment for us. However, submarines and other things that don't have the access to the environment do have these CO2 removals. A lot of these systems, both the Russians and ours, were generations from submarine technologies. I think you're exactly right. They had a lot more crew and didn't maybe worry about the labor hours to fix things, and they had more volume for spares. We are at a shortage of crew if we're spending a lot of time, whatever you said, 2 or 3 crew members just fixing things, and certainly environmental control should be taken for granted, not maintain and repair continuously. So the contractor communities, NASA, JAXA and other industries are looking at that and trying to get the advanced environmental control life support systems readied for rollout onto ISS so that we can put them in the racks and try close off modules and do some experiments and see what we have. I think the doctors and the crew have responded better to less than 3 millimeters mercury CO2 levels. So we try to keep it down into the high 2s. Less than 3, and that is taxing both systems operating. What we thought was going to be a main system and a spare that we could turn on when this one needs repair, we're actually running both systems. And when we go from 6 down to 3 crew, obviously that's half the demand, half the CO2 generation, so it's much easier. And quite frankly, this summer we've had some down to 3-person crews at a couple of stages here. And so this year has actually been a good year for CO2 levels being low, but we are taxing the systems, and right now we have several things in work just in the current systems. We understand the dusting that's going on in our CO2 removal system. That dusting is clogging valves, keeping us from turning, clogging the downstream flows. We are not only looking at the zeolite that is being crushed under the pressure that we pack the beds in, and we're changing those procedures on the current design. we're also developing improved, and we have a DTO coming up, an experiment coming up, of valves that are turning and changing the flow of the push-pull system in the CO2 removal, such that they have more power to turn and when they get dusted, and that the dust doesn't get into the stems of the valve, the seats, and the seals and things that are so important. So there's activities to expand the current system for better performance, and there's activities to make the next generation Eclipse systems that'll help us get to deep space with a high reliability and first-time success. So those things are very important, and we're waiting to deploy the new systems. We're tweaking the current systems. So there's lots going on in that arena. Thank you.
Again, so that's, again, we're talking about how to have more crew members aboard the station and add one crew member to U.S. segment. But again, if we're talking about how to more efficiently utilize the crew time, we can go back to what's Quechee mentioned before. So we can go back to stage when we train and work as one crew. So, for example, it's easily to have like crew members, like universal scientists and engineers and crew members and flight engineers aboard the station, and work with them in equal responsibility for U.S. and Russian segments for how to work with all the systems, and as well how to perform scientists on both sides. If you know, so this very long time period between the PI decided to have experiments aboard the station, and before this science have been performed aboard the station, because the create the equipment, create the procedures, train the crew members. It takes time. But now we have a good tendency. Then the scientists have like a list of like a knows what's equipment already there. It's not only for the national segment or Russian or the US, but on both sides of station. That's help to have the science program more creative, more powerful, more interesting. And I'd like to ask Irina about maybe the problem about how to the joint science performs now, and your view how to do in the future. Можно на русском.
Actually, now we have a great collaborative experiment, rodent research, and I hope the last year was very helpful for Russian side and for American side. We received many lessons for us how to collaborate with each other, but now I think that we have to understand that our main goal is scientific result. Now we try to divide the crew members' time in comparison with tissue sharing, and try to connect it with some different interests, sometimes political interests, but I'm fully agree that ISS was developed for scientific research, so scientific result is our main goal. So let's stop to divide crew members, Russian, American. It's one crew, and it's one experiment. It's not Russian, it's not American, it's collaborative experiment which could be impossible without each other crew members. So let's stop to divide crew members' time and connect it with tissue sharing. Let's start to work for scientific result.
Okay. Hardly agree. Absolutely. So I think we've got just a few more minutes. Maybe there's folks that have some questions in the audience. I think back there we do.
Hi, thanks very much for a compelling discussion. I'm Sue Bloomfield from Texas A&M University, and very interested in and very pleased to hear the support for more fundamental research on ISS from a number of you on the panel. We mentioned that, well, one obvious solution to getting more of those experiments that are already funded by space biology that have been waiting for some years to get them on board ISS, one solution might be increasing the number of crew members. Is there any other solution to this, given the difficulties in increasing crew member number?
That's a great idea. Oleg, you mentioned the one thing. We have a lot of very capable facility class, payload racks that are up there, combustion facility and a fluids facility and a whole host of other things that are up there. And I don't know if the scientific community in general thinks about it in those terms that, look at all the resources that are there, would even have the ability to get the insight in how they all operate and what the capabilities are. But if any of you were to float around space station right now, I'll guarantee, even the ones that have payloads that fly on board space stations, you'd be shocked at the capability of the equipment that's up there. I think we just tend to be more stovepipe maybe than is necessary. So that might be one way. I don't know if the panelists have some other ideas.
Yeah, yes, I agree, because for example, is I know that not many U.S. scientists have any idea about the list of science equipment on Russian side. Absolutely, but it's a huge list of that, and maybe somebody could be interested just to use this equipment and already pre-trained crew members to do science. And so that's why we start working in this direction to have like an open list for science equipment for both sides.
Great question.
Well, just to be clear, the biggest limiter to science throughput, Bill, is... What is it? Is it crew time, real estate, hardware?
Depends on the science. Crew time is a big one for a lot of fundamental biology studies. It requires rodents or some other non-human subjects, and getting those subjects up and down is really hard. Right now, SpaceX is carrying a lot of rodents almost every time it's flying. Many of those are dedicated to cases studies, and we're trying to figure out how there might be other ways of getting those kinds of test subjects on the station. I think that also figuring out linkages between programs, and we've heard a little bit about linkages between countries. Part of the ISLSWG charge is to get space biology and human research program talking with folks like the Japanese, and we just had a nice discussion about OP3 and the opportunities that might come around as a result of OP3. One thing we were talking about is getting back to the hypogravity, or the gravity as a continuum question from this morning, about having U.S. investigators supported by human research and space biology using rodents that the Japanese would fly in cooperation with Japanese scientists and spun for long periods of time on the Japanese centrifuge, so we can look at 1.6G or at 3.8G and understand the mammalian response to long-term exposure to those things. So we're looking for connections, but I think right now the main limitations are crew time and the availability of the kinds of test beds that the space biology folks might want to use.
Yeah. So if it is crew time, though, even without adding an extra person, I think if you looked at the whole crew, again, get away from segmentation, but look at the whole crew as an available resource, there's lots of times when, a group of folks are idled for whatever reason, there's just not things to do, and you could very, very efficiently capitalize on that extra, crew time that would be available for you, if we thought in those terms. Yeah.
I'll just add that the CST-100 is designed for 4 seats with a 5th seat for either research or a visitor. Certainly getting more crew up to station, as long as the subsystems can maintain the health and livelihood of the crew, adding, sleep quarters, things like that. Again, space station is equivalent volume to a 747. So when you think about 6 folks, and you guys have all been there, I have not, floating around, someone said you don't see anybody for an hour or half an hour. I mean, there's obviously volume, and if you need the scientists to actually physically do the work, there's probably specialists that we should do, and maybe it's industry specialists, maybe it's pharmaceutical company wants to have their person up on orbit. We'll train them to be, NASA will be probably glad to train them as an astronaut because they come with the other skills that can make them more efficient. And maybe they want to have their own rack, and this is an Amgen rack, or this is a Boeing rack. Some of those things could be of the future for both ISS and other platforms in LEO that would help us specialize to a pharmaceutical discovery. It's all going here. Metallurgical's over there. The science of rats and other things over here, so that we can really get efficient. Mm-hmm. And if efficiency on the ground, which we all do in our daily work, can also happen on orbit, I think there's things to benefit, and we got to look at those also.
Dr. Prashad?
So my question, actually, this is to Mike Barrett and also Bill Pulaski, was, so I've been involved in a number of VIP studies over the last 5 years, and I think one of the major gaps still is there a time duration effect? And so far, we don't know if the manifestations persist after 6 months. Now, we know that about 25% of the astronauts are developing the more severe manifestations. So one of the considerations should we select astronauts that we know are at risk for VIP and put them on a 1-year mission rather than an unselected astronaut who may, we know it's an interaction between some intrinsic effects in nature versus nurture. We could pick somebody, put them up there for 5 years. They might not develop any manifestations of VIP, and then we will not have learned anything when we send people on a 30-month mission to Mars. But if we pick an astronaut that's already developed manifestations of VIP, and that may be a better opportunity to see if that time duration is a factor. Or have somebody up there for 3 months or 6 months. If they don't develop any manifestations, then return to Earth and let somebody else go up there and sort of maximize the time that's left on ISS. Because otherwise we won't know, we might be having the wrong people exposed to the longer duration and then not know when we send them to Mars and what are the compilation of factors. So, yeah.
So let me spin it real quick, and then Bill will answer the research selection. You asked, we don't know if they persist after 6 months. Mine have persisted for 6 years. I'm case 4 in the literature. So one of the main reasons we missed VIP for so long is because it doesn't seem to have a big impact on function, performance. And although you don't know what you don't look for, you don't find what you don't look for, we've been dorking around in space for 50 years, and the potential problems, vision loss, visual field loss, cognitive disabilities and whatnot in later life do not seem to be a hallmark of the long-duration spaceflying population. We, as a group, tend to live long, very productive lives. So it's partly, I'm keying in on your use of the word severe symptoms. So what does severe mean? Does that mean anatomically expressed to a greater level, or does that mean with more severe clinical implications? So again, that part of why we missed it is because it doesn't seem to impair us or slow us down or affect overall health and longevity. Now, I may eat my words when we start doing more tight surveillance, but that's why we're still flying long duration in space now instead of doing a stand down to figure out, which we would do if we were a piece of hardware and acting this way that we didn't understand. We wouldn't fly a rocket if a critical piece of hardware were acting like our neuroanatomy does with VIP. So, okay, so did you have a follow on that?
Yes, I mean, maybe severe is not the right word, but there's the VIP classification, and we know that only a small percentage will have the higher classification. What we don't know is if we take somebody that has the higher classification, increase the duration of time in the exposure. Now, sure. I know you mentioned you have had it for 6 years, but you haven't been, obviously, in space for 6 years. But if we have somebody who, after 6 months, develops class 4 and keep them there for another 6 months, will it stabilize, or will it go to even a higher class? Right. And that's, I think, what we should know before going on. I think that's a missing piece of information.
So we, Crew members are selected to fly for multiple reasons, and it would be a fairly significant change in paradigm if people were going to be selected because they had peculiar physiology that we were interested in. So I mean, Mike can talk to that better than I can. We're not usually consulted when people are selected for flight. Nevertheless, there are two pieces. One, I think that we are interested in whether there's a temporal duration, which is why we want to have additional one-year missions. So we'll have another 10 crew members that will fly, and at the current rate, we should see 3 or 4 of them that develop VIP, and presumably some of them will have already had manifested VIP on previous flights, so we'll know what to look at. The other thing is, and what's really kind of perplexing in this whole thing is we cannot develop a ground-based model for VIP. And that's really a hard question. You know, we think if we really think that VIP is related to fluid shifts, then why don't people get VIP when you tip their head down and you simulate the microgravity that we've used for all other physiological responses of space flight for 3 or 4 decades? And I know that you're familiar with this issue, but it's a perplexing problem. You know, it's probably more complicated than we think it is. It's not just fluid shifts. There's something else going on, as Mike was alluding to before. But you know, one of the things that we typically do with trying to understand these kinds of physiologic responses is have ground-based analogs where we can thoroughly understand the phenomenon before we go into space and use valuable crew time and resources to try and understand it. So, you know, I think I'm looking to the research community, your team and others who are looking at the VIP problem to try and figure out, you know, what's really going on, what's the most likely hypothesis, and what do we actually have to go to space to test, and you know, and then we're happy to go and do that. In the meantime, while we're doing this, we'll extend the duration of missions for a number of crew members and try to understand and do phenomenological studies. But it would really be better to have a mechanistic study underneath it, so that when we go to space and use those resources, we're actually going to answer a question that we're pretty sure we're going to get, you know, a yes or no, up or down answer to.
That's a good question.
I think we have maybe just time for maybe 2 more very quickly. I think space station orbital mechanics dictates that we end close to on time because we have a downlink. So,
my question is, do we think that we need artificial gravity to get humans to Mars, and are we using the space station to answer that question?
Go for it, Bill.
It's not a short question.
Yep. Artificial gravity comes around quite frequently. Here's what we know so far. We are able to protect crew members on station. We're able to protect crew members on 6 months missions, bone, muscle, cardiovascular function, to an extent that they're able to function quite well after flight. From a vestibular sensory motor perspective, there are some issues immediately after flight that persist for a period of time. And there's no, apart from the vestibular issue, which is, again, temporary and resolves itself, there doesn't seem to be a driver at this point for using artificial gravity. We are, however, we have started a new program in looking at artificial gravity in ground-based studies because of the VIP problem. If VIP actually turns out to be related to fluid shifts, as we think it is, and it's intractable using other techniques, then we may actually need to go to artificial gravity. And so we're looking at trying to figure out how we would do that. We probably won't be spinning vehicles. We'll probably be spinning either part of a vehicle or someone within the vehicle, and what would be the appropriate prescription. But again, you know, until we have a driver and a VIP becomes the driver, then we have to understand what kind of artificial gravity therapy would be required to resolve VIP. And without a ground-based model for VIP, it's going to be hard to get answers to that question again on the ground.
I think Dr. Gushin was next.
Thank you, Mike. Very short and pragmatic question. 5 annual flights of NASA. How much is this issue is coordinated with the Russian side? Because I think the idea is there must be pair of subjects, Russian and American, both for annual flight. Is it true?
Absolutely. I'll ask John Charles, who's been working this with Dr. Bogomolov, to respond to that.
These are about the one-year missions, additional one-year missions.
This is additional
5 more
one-year
for a total of
missions.
10 more subjects.
And how much are we coordinating with the Russians?
Yeah, it's a good point. We have an actual
Yeah, there'll be a dedicated panel
to
for
one-year
that.
missions.
But great question. And maybe we have time. General Stafford, our last question.
You know, having the fortune later on to manage some giant missions when I was the Air Force Deputy Chief of Staff for Research, Development, and Acquisition, I look at this, and, you know, we've talked about all the great things it's doing, but to me, as I pointed out, where Gemini was so critical for Apollo, well, this, to go to Mars, this is kind of like a part of a Gemini.
Yeah.
In the same way the lunar surface. So you put the space station with the lunar surface, in that way is like Gemini going on to Apollo, or this is going to Mars. And this is why this is so important.
Yeah, therefore it's not.
One final thing for just Bill. I remember from the study that George and I did, we had the Department of Energy there with a lot of great talented people. And as far as solar radiation, I think they said we are completely protected if you have 16 grams of water per centimeter cubed, which is about, to me, from a country boy, about 1 foot of water. Mm-hmm. Is that about right?
The way we'll do that is probably with aluminum or something on the outside and then a water bath inside, but the total amount is 20 grams per centimeter squared that we're looking at as the optimal amount right now. And it depends on what material you're sending it through. I don't know what the depth of polyethylene or aluminum for the surface of the vehicle. But yes, we have actually a very robust program at Brookhaven National Laboratory looking at not the solar particles. We're not concerned about. It's GCR, and we can simulate GCR pretty well now. We can do full field GCR simulations starting two weeks ago with the studies that we're doing.
Ballpark here, the moon or beyond. How many millisieverts a day do you get out there?
On station? I'm sorry.
On station,
going
are you
to the
asking?
moon, did you say, in deep space?
I mean, above the Van Allen belt. I'm the only one around here who's been above Van Allen. But how many millisieverts transit on the way to the moon and Mars?
Yeah, 1 to 2. We get about a half a millisievert in low Earth orbit on station,
I know you
and
get
1 to
about
2
a half
outside.
millisievert. But beyond...
1 to 2 is as we have our...
Yeah.
But 1 to 2 millisieverts per day.
Per day.
2?
Yeah.
1 to 2.
Thank you.
Okay, so I think we've run over. It's about all the time we have. Thank you so much for the great questions. The panelists, I'd like to thank you very much, and we'll get to have a lot more discussions on the side. Thank you.